Today I'm going to be introducing you guys to how to look at the efficiency involved with various data structures, two of which you have been using and are probably pretty familiar with at this point syntactically. Another that maybe you're not so familiar with, sets. So just to briefly go over the syntax, I know you guys have been using lists, but so lists, you have a data structure that stores elements in a specific order. So this is how you would initialize or add things to a list. So you have this candy list. We have, okay, there, yeah. We store them in the specific order. So Kit Kat is in the first position, Crunch in the second, Kiss is in the last. You can append. And that's what the whole candy list looks like. If we want to access a specific element, we can do, for example, that'll give you the second element because the counting starts at 0. There's pop, which will remove things and return them. And we can also pop from a specific index. And then if we want to look at the length of a loop, we have this method called len, and we can iterate through it and print them one by one as well. So these are operations that I believe you guys are familiar with, but I just want to go over them because that's going to be important when we try to understand the efficiency of what's happening behind the scenes with these operations. So under the hood, lists correspond to what are called arrays in many other languages. And the way arrays work, in Python, a lot of this is obscured because Python is a very high level programming language. But behind the scenes, what's happening is that Python has to find in the computer a specific area of memory to put these objects in. And then when you have that list, those objects will be stored consecutively in memory, meaning they're all next to each other. So in memory, you're going to have a certain amount of space allocated to each element. And the first block of that size will be for the first element, just index 0, then index 1 after it, and so on. So when you create a list in Python, what's happening behind the scenes is that Python is telling the system, your operating system, hey, give me this block of memory that's this length. And that length will be depend on the initial size of the array. And so it's a little more complicated than this, but let's just pretend that, for example, it just asks for a specific size, which is, let's say, 10. And that's our initial list length. So now if we just create it like this, okay, so you have one element in it, but because we might want to add more elements later, it's gonna ask for a block of size 10. And when you access that first element, what it's going to do is it's going to go to the start of the array in memory and check what is there. And so that gives us this pretty simple formula for calculating what's at any given index, right? So if we want to get to the third index and we know that a block is 8 bits, how would we find that? Well, if we initialize our array at memory spot 100, and we want to get to the third place, and each place is 8 bits long, we would add 3 times 8 to the initial spot. And so that means that no matter where we want to access an element here, the operation, like the cost, how long it's going to take to calculate where in memory that object is always going to take the same amount of time because it's just addition and multiplication. All you do is check what is the where's the array start, which element we want to go to, and then multiply by the size of each element. So this is for example, for the fourth element, right? Because we started 0. So we have this very simple formula, and if you want to access anything in the list and we're not adding or removing anything from that list, it's very quick. It's what we call O of 1, which means constant time. No matter how big that list is, no matter which element we want to access, it's always going to take the same amount of time. Now, where we run into trouble or where we need to think about things a little more carefully is if we want to change the size of the list or add things to it beyond the size that's already been allocated. So initially, as I said, Python allocated space for 10 elements, right? And those are somewhere in memory. Now, the way that works is that block of memory, we don't know what's ahead of it and we don't know what's behind it. The operating system hides that information from us. And if we try to access information that's out of bounds, we won't know, like we might be touching some sensitive information. We don't know what's there. So Python, a language like Python that's very high level, won't even let you do that. And so what happens is, suppose that we want an 11th element. Now Python has to ask the operating system for a whole new block of memory that can hold at least 11 things in it. When I say it can hold 11 things, that's how much memory is that? That's 11 times the size of one element, which we're saying is 8. So it needs something that's 88, whereas before it was only 80. In practice, when you expand a list, Python won't just expand about one at a time. It'll ask, I think it doubles it at any given time that you might expand the list. But we'll just say, say it just asks for one at a time. That means that every single time you add something to this list, it has to ask for a whole new block of memory. And now that it has this whole new block of memory, well, it has to copy the old elements from the old block of memory into the new one, because now the whole array has been moved somewhere else, and so that we can add more elements to it. So you can see why they can get really inefficient as we keep resizing the list, right? So this is fine if we have lists that are always going to be the same size and we don't really care about anything like adding or changing anything about them. Or if we only ever want to change what's in a specific position. But if we want something that can grow easily, if we're dealing with a large amount of data, we're going to have to look beyond this, because we said that this operation is O of n. N here means the size of the list. And so if you think about it, if every single time you want to add an element, you need to copy that whole array over again, you need to do something for every element in the list. So you're doing something for n times, where n is the length of the list. So we say that's O of n, meaning the time that takes is proportional to the length of the list. In practice, there are some things that Python happens to do to make this a little more efficient than that. But in general, we're talking about O of n operations here. Now, so the reason this happens is because if we look at our formula for accessing elements, right, we have the memory location of the element, and we access it because Python knows the array start address, and then we give it an index number. So it does this little formula. But you can see that because this is just addition plus multiplication by the number of spots that you want to go to, that this depends on the elements being sequential. Now you can imagine, what if we did it a different way, where elements were not sequential, and that we had some kind of formula that allowed us to go exactly to where any given element is with a single operation, right? Meaning that we don't need to know what position it's in. We just have one formula that takes in what element we want and gives us where it is in memory. Now that seems a little abstract right now. I'll show you what that actually looks like. But the idea is that instead of having a function like this, we're going to introduce this concept of hashing. So there's a type of data structure called a hash table. In Python, they're called dictionaries. In other languages, they're called sometimes, very frequently, hash tables or something like that. Sometimes maps as well. And the idea here is that instead of having this function, so I rewritten this as a function, so you can think about it as a function the way you write it in Python, or a math function, where you get a memory location depending on the index, right? That's what's going on here. Instead, we're going to access memory location, not based on index, because index is the relative position, right? We don't want to do that because that will require us to have consecutive memory. Instead, we're going to access memory just based on the name of it. We're going to have some kind of identifier associated with the data we want to store. And then we're going to have some kind of function that tells us, hey, here it is in memory, solely based on the name of the identifier of the element, not based on how it is positioned relative to anything else. And so you can see here that if we want to add more elements, we don't need to copy over the whole array. Everything else stays in its place because the hash function will always return the same value for a given identifier. All that's happening is that now the hash function will give us a different value for that new element, and Python will just return that to us. So we don't have to worry. So we don't have to deal with the inefficiency of copying over the list. One thing to note here is that traditionally in Python, dictionaries were not ordered, hash tables are not ordered. And the reason was because, as I was saying, memory elements are not necessarily consecutive. It's still true that in a dictionary, memory elements are not consecutive, but the implementation of the Python dictionary does mean that the way they're exposed to you, the way you would actually use a dictionary, the elements do happen to remember the order that you inserted them in. We won't worry about that right now because that doesn't actually affect the efficiency of operation. So we're going to treat it as if the order doesn't matter with dictionaries. Okay, so I'm going to explain in a little bit what that hashing function looks like, because right now this just seems a little obscure. Like, what does this actually mean? But first, I just looking at the syntax, which you might be familiar with. So in Python, if you have a dictionary, right, you have a key and a value, and then you can initialize them like this. So for example, we have this KitKat variable that's a dictionary. And then we have these keys that are on the left side of the colon, and the values that are on the right-hand side. And then if we want to access a given element, we access it by the key. And so if we think about it, what's happening here is that this hash function is being called on the key. And that gives us some memory location where the value is stored. So that's the relationship. So you might have been using dictionaries, but you might not necessarily know that this is what's happening. This thing here is mapped, a string in this case, is mapped by some, and usually, very frequently, dictionary keys are strings, but they don't have to be. Now, what's nice here is that so far, I haven't actually told you what a hash function will look like. And that's because for a lot of Python types, for example, strings, and basically almost all of the basic Python types, the hash function already exists, meaning that you don't really have to worry about that. Python already has some function that will map a string to some position in memory where this value, Nestle, or this value, 200, is stored. And so in terms of the actual syntax of the operations, it's pretty similar to how you would do list. It's just that now we deal with two values, right? Because we need a key, whereas before we had the index, now we have a key. And then the value is what's stored at that key. And so if you want to update things, now notice that now remember, the hash function here maps this key to some value. That means that if you want to change the value for some key, that key has to remain unique. You can't have multiple keys in a dictionary because this hash function, it won't know what to do, right? Like it doesn't know how to differentiate the two. All it knows is you have some key and that points somewhere in memory based on this function. But if you can't store multiple keys because it'll return the same value for you in memory here. So that means that, for example, in terms of the keys, whereas in a list, you could have a list that has the string KitKat 3 times in it. You can't have like here our key is brand. We can't have like 2 keys that are brand. Instead, if we try to like change something, we can change. Instead, what we can do is we can just change the value that's associated with that key. So that's what's going on here. And so now if we try to access now a key that's not in the dictionary, Python gives us this error, right? Because KitKat, we put in a serving size here, but we didn't for Kiss. So that's just saying that our hash function doesn't know what to do with this because it's not associated with anything yet. We could add it the same way we did here, and now that's telling Python, hey, run the hash function on this string, go to that place in memory and insert this string. And so if we did that, then this wouldn't throw an error anymore. So a quick analogy on how to understand hash functions. If you guys are familiar with the Dewey Decimal System, this is a rough sketch of what it looks like. The idea is that every hundred or so section of 100 or so numbers is associated with a specific category. And the idea is that if you have a book's category, you can find what section it's in, like immediately. Like you'll know exactly. Like if you know you want to find a book about religion, then you know that it's in the 200s. If you want to find a book about literature, you know it's in the 800s. You don't have to like start from the very first spot in the very first shelf of your library and keep searching until the end, until you find. That's what you'd have to do, for example, in a Python list. If libraries work like Python lists, you'd have to go through every single shelf and just hope you got lucky eventually. In dictionaries, though, that's not the case, right? Like with the Dewey Decimal System, suppose you wanted to find, let's say there's some, I mean, Dewey Decimal System is supposed to be comprehensive, but suppose there's some other category like, I don't know, aliens. Okay. Now, that's not actually here, but we know that because we know what the keys are. The keys are this: computers, information, and general reference. That's one key. Philosophy and psychology is another. Religion is another, and so on. So we know that if a given key doesn't exist, we don't have to go looking for it. We already know that that can't possibly be there. Whereas with a list, if you want to search for something and say it's not there, the only thing you'll find out the only way you'll find out if it's there or not is to literally go through the entire list. And for short lists, that's not such an issue, but you can see how with very big lists that can become quite the problem. Now you might think like, okay, so right now the way I've outlined this here, right? We can store one book in one index, and that index is just like the first element in that block of 100 numbers. But say you want to store another book there. Now, this is where things get interesting. Now, the thing with hash functions is in theory, ideally, you want every single possible key to return a single value, and for the hash function to return a single value, and for those values to be unique, meaning that if you have multiple keys, they don't give you different, like if they don't all give you the same spot in memory. Because you can imagine if that happened, if you had the same spot in memory but different keys, then you wouldn't know which one to look for there, right? So that's what happens here, like with our Dewey Decimal System. Suppose we want to store a second book here in the 500s, which is science. Now we already have the Introduction to Physics book. Say we want to add an Intro to Biology book. What's going to happen is that we're going to have to like sort of store a list at that position in memory. So at that position in memory, on the outside, it's still like working like a dictionary, meaning if you have the key, you can go to like any of these indexes. But once you get there, if you have a collision, a collision means that you have multiple keys mapping to the same memory address here. If that happens, you're going to have to search through that list the same way as you would with an array. And so what you want ideally is for every single one of these slots to have just one element. In practice, depending on the object, that might not be possible. But when you design a hash function, which most of the time you don't have to worry about it, but if you're in the position of having to design a hash function, you'll want to think about it like, how can I minimize the number of collisions? And that means thinking intelligently about what kind of data you have and how to organize it. And so Dewey, when he designed the Dewey Decimal System, did this. It turns out the actual Dewey Decimal System is much more granular than this, meaning that you don't just go to the 100 section for a category, you'll then go to a more specific section depending on the subcategory, and then an even more specific section depending on the author. Which is why, like, if you go to the library and you ask the librarian for some specific book, they don't just like start from the beginning and go through every book in the library. They don't even go to like a specific section of shelves and look for that book. They'll go to a very, very specific spot on that shelf. And maybe within 4 or 5 books that you can think about like that as a hash collision, they'll just search through that very small list. And so ideally you want a hash function that does the same thing. It doesn't just return, like in theory, you could have a hash function that just returns the same value for every single key. That's a really bad hash function because that means that you're basically just having a list there. It's no different than having a list. You just have a consecutive block of memory. On the other extreme end, as I said, like you have an ideal hash function which maps everything to a unique value. In practice, you're going to fall somewhere in between those extremes. Okay, so
let me jump in just for 1 minute.
Yeah, sure.
Yeah, I was thinking of something while you were saying that. Oh, I can't share my screen. So sad. So one thing I was thinking of was like, let's say we have like a key of
Mhm.
like, for religion, we have like a key of God, right? So
Yeah.
now,
Mhm.
and we say like, okay, our hash function is going to be, letter G, what number in the alphabet is that, right? Let's say it's like, I don't know what it is. Maybe it's 6, right? And
Two
O is like
hundreds. Yeah.
15, and then D is like 4, right? So now you add them up and we get like 19, right? Well, that is a hash function, and that's like an okay hash function, I guess. But we can think of problems with it, right? Like one problem. So with that hash function, we're like, all right, well, like go to location 19 in memory, right? We have this key of God. We count up the value of each letter. Go to adds up to 19. Go to position 19 in memory. Every time someone does like our dictionary square bracket God, we know where to go, right? Of course, you can think of problems with this, right? Like if we spell dog, right? If we go to a key of dog, that will give us the same value of 19. So, right, that's our collision. So, like,
Yeah.
right, like what you want with a hash function is it has to be more complicated, right? Complicated enough so that those collisions don't occur. But we still know that as a function of our key, we know directly where to go in memory.
Right. And so when I said like thinking intelligently or data when you're designing a hash function, suppose you know that like there's no anagrams, then just there's no like it'll never be the case that your data has both God and dog. Then Jeff's hash function works fine. Jeff's hash function only runs into issues when you have like the same letters in different orders for different entities. So you have to think about it. Does this hash function work for the data that I have? For simple data types, as I said, Python already handles this for you. The reason this is important to think about, by the way, isn't just for Python dictionaries. Hash functions show up in a lot of places, many of which you may have to deal with as a data engineer. To give an example, when I was working at Amazon, one of the projects I worked on was because when my team's service initially launched, they were using, they have been using a NoSQL database. And NoSQL also uses hashing functions. And it turned out that at the beginning, when the service was launched, the team had not designed a very good hash function. It had many collisions, which at the time weren't an issue because the service was small. But like 9 years later, we were having a lot of lag because customers were having all these collisions. So one of the things I had to do was redesign our data to deal with that. So thinking about like what makes a good hash function is actually an important skill that shows up in many places, not just with Python dictionaries. This general idea of like mapping some key to a unique spot is something that is very common in software engineering and data engineering. Okay, so I'm going to say a few things about sets too, but does anyone have questions before I do that? I can't see video. I don't know. So if you do, just speak up. Otherwise, okay. So one thing is when I introduced dictionaries, I pointed out that now you need a key and a value, whereas before you just had the index and the value with lists. Now you might say, okay, so dictionaries aren't just more efficient lists; they also have these two values. Suppose you don't want two values; you just want to store like a list of things, a collection of things. But you don't care about like there's nothing else associated with it. Now, one way you could do that, you can think is like have a dictionary where you have keys but no values, right? Now, that just means like it's just like extraneous, that extra information that you're not going to use. So Python has this other data type called a set. And a set is kind of like a list in that you just have like a sequence of elements, but it's like a dictionary in that order does not matter. But like it's like a list in that it's only the key, it's not the value. So oops, so if you look at it like this is how you initialize it. You can see it's very similar to a dictionary. You have the curly braces on either side, but whereas with a dictionary you'd have like a value like that, with a set you just have this and that's it. And this is how you would add to it. So now you can see Candies also has M&Ms. Now notice something, the M&Ms got added to this second to last position here. And in fact, this could be in a different position every time this runs. In practice, it may or may not be the same. We don't know. The point is you can't like depend on that. We don't know what order it's going to get added in. And so if you iterate over them for candy and candies, will this happen? Okay, so we've gotten lucky the 3 times I just ran it. It just happened to be the case that I returned the same order. But in practice, actually, it turns out sets, you can't know this. It could be a different order every time, which is fine in many cases. You might just want to list something where you don't care about the order. The other thing is, remember where I said dictionaries have to have unique values, and that's because the hash function will just map some value to that. And so you can't have multiple keys because the result of the hash function will be the same. In the same way, sets also have a hashing function. It's the same thing. It's just that the difference is that wherever that is in memory, we don't care about what's there. We just care about the fact that we have this at all. So in that case, like as with dictionaries, you can have duplicates here. So if you did this, actually, let's just see what happens if I do Snickers again. The result is exactly the same. If you try to add the same element many times to a set, it won't change its contents. And actually, I don't know if you guys saw it, but just there, when I ran it the second time, the order shuffled a bit. So you can see the order changes. This is actually, now you might say, oh, well, okay, sometimes I want the order, sure. But sometimes the order doesn't matter. And not only that, you actually want to remove duplicates. So a very common pattern is, say you have like a list. We'll do a, and you actually don't want duplicates. What you can do is convert that into a list like this. And that'll remove the duplicates, right? So it's very convenient if you want to remove duplicates. This is a very common pattern you'll see. Okay, yeah. So yeah, that's an overrun. That's an overview of hashing, while we have hashing, and the data structures in Python that implement hashing. But as I said, you'll see hashing in many places.
Cool.
Yeah.
That's great. Yeah, thanks so much, Abhinav. That was awesome.
Mhm.
Yeah, and just to do like a quick review. So okay, if we're thinking about like finding elements in different data structures, right? So if we have like a list of elements, say we have like the letters, right? We want to find the letter D, right? What's the cost of finding the letter D in a list of letters, right? That's big O of n, right? We have to go through every single element in the list to figure out whether or not it's there, right? Now, if that's a set, what's the cost of doing that? That's big O of 1, right? Because that letter D is going to get passed to a hashing function, tell us exactly where to go, right? And we can just go there. It's either there or it's not, right? So regardless of the letter, we will always just, with a set or a dictionary, just pass it through the hashing function, figure out where to go, right? So something like that is, very good. Like finding whether or not something is in a collection. It's like dictionaries, lists can be very useful. So what are lists good for? Like order, right? Like we talked about, right? Like sorting things. And remember, something like the min or the max, after you sort a list, just go to the very beginning of the list, go to the very end of the list, right? After you sort it, it's big O of 1, right? To do that, because you just have to go to one spot to figure out like something like what is the min or the max. All right, cool. All right, so what we have, I'll deploy the readings. Take your time, with these. See like that they make sense to you. Feel free to ask questions. And then, and then there is like this histograms reading and